Hello, folks. We're going to work a few problems from AP old tests to sort of illustrate the conservation of energy and how you might be tested on it. So, as you can see to the right, I've got problem number 15 that asks us, from the top of a cliff, a ball is thrown horizontally with a speed v0. Which of the following graphs best represents the ball's kinetic energy as a function of time? So what I'd suggest as we work through is that you pause the video once we've got the question read, and then listen to the video to see if you got it right, and listen to the explanation. Okay, so mental image here. So we've got a ball, softball, baseball, and we're launching it with V0. And we know the path is going to look like this. So this is our displacement. The displacement would go here to here. The actual position is the curved graph. But this question asks us about kinetic energy. So, kinetic energy is directly related to mass and velocity squared. And in this case, we have a starting velocity. So when we go to make our KT graph, K has to be a positive number. So we have to start with some amount of kinetic energy to start with. As the ball falls, gravity is going to accelerate the ball vertically. So the ball's speed will be increasing. So as it falls, velocity goes up, which would mean kinetic energy goes up. But the relationship is a parabola. It looks like y equals x squared. So my graph is going to curve up. Now we don't know how much, but we do see there's only one graph that fits this situation. So that's a pretty typical graph question. Here's another one. Let's look at, let's see, number 20 is what I was looking for. So number 20, you've got a figure shows a rough semicircular track whose ends are vertical height h, and we're going to put a block. Notice it's a block, not a ball. Placed at point P at one end of the track, slides past the bottom, comes up on the other side, and they ask us to estimate the height the ball will rise on the other side of the track. So I'll let you think about that for just a second while I draw. The key word here actually is rough. So if I put my box right there at point P, if this track is rough, we have friction. And often, that's how they're going to tell you there's friction present. That'll be the only thing they tell you. So, in an ideal world, no friction, the block would come all the way back to same height. But friction is going to slow us down the whole time. And so due to that, your block is going to end up at a lower height. So if this was your original H, it's going to be somewhere between here and here, but without numbers we can't tell you any more than that. So the answer here again would be D. Alright, couple of pretty traditional AP problems. And we'll work on springs and pendulums later. They like to ask energy a lot when you're working with springs and pendulums. But we're going to look at a couple of problems that we can use with conservation of energy. So let's look at this one. Very similar to the last one, you'll notice, but now it's free response. So 1975 B1. Give you a minute. You can pause if you need to read the problem. But what we've got is we're going to do the same thing we did just last number 20, except we don't have friction until you get to the bottom. Okay? So the things we know is the mass is 2 kilograms. We're told the shape is a quarter circle. Radius is capital R. And then the horizontal plane is 8 meters from the beginning. Let's see. It comes to rest 8 meters from the beginning of the plane. Okay, so our X final is going to be 8 meters. The curve is frictionless, but there's an 8 Newton force of friction. So force of friction is going to be a constant 8 newtons while it's sliding horizontally. And of course they tell us G use 10 meters per second squared. Okay, 1975 you didn't even have a calculator, so that makes the problem more fun. So the question is, how do we work this problem? Well, what I see is the ball falls, or the block falls along the curve. And kinematics looks like it would be terrible to have to deal with that. So I would rather not do kinematics. I'd rather use energy. And we know energy is conserved without friction for this problem. So, as it falls along the curve, what I'm going to use, the information I'm going to use, is that the change in potential gravitational energy will be equal to the change in kinetic energy. So that'll help us know how fast it's going when it gets to the bottom. Okay? That's how I'm going to attack the whatever the question is about that. And in this case, it says determine the magnitude of the acceleration while the block is sliding across the horizontal plane. All right. So, let me get a new page. So I'm going to, part A is going to ask about the end of the problem instead of the beginning. So, A. And they asked me for acceleration if force friction is 8 newtons. Okay. We also know we travel 8 meters. So our question is, how in the world can I figure out the acceleration? Because we know force equals mass times acceleration. But I can't just say 8 equals m, which is 2, and a, which is unknown. Can I do that? Or do I have to use something about another force in the problem? Well, let's look back, and I'm going to do some thinking out loud. And then I'll show you how I actually attack it straightforward. So then my question is, I don't know if I feel comfortable about this. This is me modeling how you're thinking. So then I go, well, what about kinematics? I know x final equals 8 and x original equals 0. We can call that the start of the rough part. But I have an initial velocity that I don't know. I have a final velocity that I do know because we're stopped. Acceleration, don't know. Time, don't know. So do I feel better about that? And I don't know. So this problem originally, when I looked at it, it felt like conservation of energy. So I'm going to take conservation of energy approach. So this is cute and nice, and I may need it in a minute. I'm going to shuffle back to what do I know that's a key idea in this class? Work is change and kinetic energy. That's a key. So work is force times distance equals 1/2 mv final squared minus 1/2 mv original squared. Now here's where I can feel like I'm standing on solid ground, because the force that causes me to slow down, friction causes me to lose energy. Friction causes me to slow down. So force of friction would be the one we're talking about. So I have 8, and the distance the block travels is 8. I know that the final velocity is stopped, and the initial velocity is unknown. That's okay. So here we go. 64 equals 0 minus 1/2 times 2 times the original squared. Okay. So these cancel. So my original velocity is 8 meters per second. Is that what the question asks for? No, it's not, right? But now I can finish the kinematics with this. The final, do I know how much time it took? No, don't know that. So was this approach the short, easy one? Now I'm coming back and thinking, I'm going to have to do more work down here. So let's draw a free body diagram. Okay. Force friction would be back. Force normal. Force gravity. Force gravity would be 2 times 10. Force normal is 2 times 10 because they're balanced. So the only horizontal force in this problem is friction. So this time, even though the problem is setting me up for conservation of energy, it doesn't do that on part A. Part A, this really simple piece, is what you're supposed to do. Now notice, I had to check that there wasn't another horizontal force. We drop it at the top, gravity pulls it down. But once it gets horizontal, gravity is no longer working with a piece that kind of points it to the right, because it's having to slide around the curve. Now the only horizontal force is friction. So that first idea was actually the best one, but sometimes you stumble around. I want you to understand that happens. It's just part of it. Okay, so letter B. How much time elapses while the block is sliding horizontally? Ha-ha! Now, all this work we did here is now going to come back into play. Because now, I can go do that work and use kinematics, which is what I was thinking about as well, here. So final velocity, it stopped. Original was 8 to the right, so positive. Acceleration, now we have to be careful. Acceleration is 4 to the left. Okay, 4 to the left, because friction would be opposing the motion. So the block is moving that way, but friction is opposing that to the left. And now that's really cool, because the math here is really easy. So 0 equals 8 minus 4t. 4t equals 8. So t equals 2 seconds. But you had to have this and that. So back in the 70s, I was in elementary school, but in the 70s you didn't have anything but a scientific calculator, if that. So they were very necessary to show every step. Now, this would probably, you would need to show either one of these two, this one and the one boxed, and then show this and the one boxed. Okay? So they're going to shorten that up and make the value of points a little bit lesser. So in the 70s, they also, the problems had how many points they had. Now it's standardized that every question is either a 7-point or a 12-point. This would probably be in a 12-point. Okay, letter C. Calculate the radius of the incline in meters. All right, well, I'm going to go back down here, because now I'm going to use that first part. So C, change in potential is equal to change in kinetic. All right, once again, energy was conserved because there was no friction. All right, so what is the change in potential? mgh original, whoops. We always do potential backwards, but if you put it in absolute value bars, you can do it like more normal. So here we go. 2, 10, 2R. Excuse me, not 2R. 1R. It's a quarter circle. Come back. because the height above ground is 1 radius. Then we end up on the ground. We're letting, that's how we're setting our 0 place. And then over here, we know that the final velocity was 0. It's going to have some bars. But the original was 8. Excuse me. What am I doing? That goes backwards. When it gets to the rough part, it's going 8 meters per second. When it started, it was going nothing. Because we're doing from the block at the top of the curve to the start of the rough spot. So here's our, this is 0, this is 0. So we get 20r equals 8 squared. So r is 64 over 20, which is 32 over 10, 3.2 meters. So part C was actually the conservation of energy state that we kind of anticipated. B and C both, but from attacking them, it did a little bit different way. Okay, feel free, do what you need to get it. Let's do one more. Okay. Let's actually do the next one, because I didn't get to be there with you during circular motion as much as I wanted to, well, at all. So let's work this one. Okay. I'll let you read it. And I'm going to make a sketch for myself. Says mass M. Distance L. Okay. So, first question. This should be old hat by the time we get to all of these, okay? So, free body diagram for the ball, okay? The object. So, what do we have? Force tension. I'm going to call this force tension 1. Force tension 2. Force gravity. Maybe a little shorter. Okay. Any other forces? No normal. We're not moving, so it can't be circular. No spring force. No, what else? Applied force. Just a straightforward tension problem. Okay. So we've got that. Letter B. Determine the tension in the cord before the string is burned. Okay. So the cord is this one. This one is the string. Okay. So tension in the cord. So what am I going to be looking at? on my working diagram, remember, no math on real free body diagrams. Got this. And I can see that this vector is made up of two others. So this will be a 60-degree angle, as you can see in my original picture. And then this leg that pulls up, force, tension, 1 up, is going to have to balance gravity. So the sum of our forces is 0. This is horizontal forces. The two forces are force gravity down plus force tension 1 up equals 0. The force gravity is mg. Force tension 1 up. Now it's just the leg. So it's going to be the y value here. So it'll be y over force tension 1 up times the sine of 60 degrees equals 0. I'm doing this one because you have to be comfortable with just symbolic math. Okay, there's a lot of stuff going on here. So I'm going to move the mg to the other side so that I now have sine of 60 it's not force tension, it's just force tension 1 sine of 60 is square root of 3 over 2. And then on the other side we have mg. So what are we going to do? We're going to cross multiply. So let me get a new page. So I have y square root of 3 over 2 force t1s equals mg over 1. So two mg force t1 force t1 equals, whoops, always write our numbers first, square root of 3 y over 2 mg. Nowhere in the problem does it tell us the mass, so that's the best we can do. But that part would probably be 4 or 5 points, because you have to have this and you have to have this. Then you're probably going to need one of these other steps, and you have to have that. And so, yeah. That's B. Letter C. Show that the cord is strong enough to support the object before the string is burned, is also strong enough to support the object as it passes through the bottom of the spring. Well, crud. Right in the middle of this perfectly nice little problem, they threw circular motion at us. So, let's get that image. We're going to start here. And it's going to curve, maybe not that far, to about that far. So here's where we start. Kind of think it's going to swing out over there. So they're asking me, at this moment, is this force big enough? Well, let's draw a new free body diagram. What forces do I have at that single moment in time? I have force tension 1 is up. Okay. We also have force gravity down, and it has to be slower. Must be unequal. Otherwise, when we got to this point, it would move in a straight line. Doesn't happen. If you swing your keys back and forth on your lanyard, they don't get to the bottom and go in a straight line and your lanyard stretch. It doesn't happen. So this is a circular motion problem. So then the thing I ask myself is, where is the center of the circle? Well, the center of the circle is up here, yeah? It's got to be up here. This is my center. So this is some sort of, circle like that. Which means some of the forces vertically is MAC, centripetal. Or you could write mv squared over r. Those would be equally appropriate. Okay? Mass we don't know. Acceleration centripetal is v squared over r. And our forces that we're adding together are FT1 up minus mg down. Okay? Alright. So, let's see what we got when we fill everybody in. Now we got to figure out one more thing. We need to know the radius of the circle, and we're going to need to know what this y is. Okay. That we can figure out pretty simply. So first of all, let's look back up at the original picture. Let's make ourselves a right triangle with a hypotenuse of L. So what is y? Okay. Y over L is sine 60. So y is L sine 60, or L square root of 3 over 2. Okay. And the radius is going to be L, because that's how long our string is. Okay. Armed with this knowledge, let's go creative space. So, we have square root of 3 over 2 times 1 over mg times y minus mg equals mv squared over r. It's okay. It's okay. He's got it. So, 3 over 2, 1 over mg, and where were we? Y is L square root of 3 over 2. Minus mg mv squared over r. Okay. Whoosh. So, here we go. 3L over 4mg minus mg equals mv squared over r, and we're going to change out r for L. What were we trying to find again? We're trying to show that this side is at least as big as that side. Okay? So we're going to need more space. Okay. Now, this is a lot of work. Starting to wonder if I'm going to be able to do that. So we've got the cord, and I need to show that the tension in the cord, I need to show that this is bigger than the weight of the object. So let's back up for a second. We were getting very bogged down in using Newton's laws here. So I'm going to tell us this is how I would have worked the problem back when I first started in physics. I probably wouldn't have gotten this far. I would probably have gotten the first step and gone, yeah, no, I don't know what I'm doing. But I'm telling you now what I'm going to do is look at this and step back. What does the question ask? It asks me to show that FT1 is bigger than mg. Okay, I can do that. Let's go back to this step. Here's how you should work this problem. FT1 minus mg equals mv squared over L. Force T1 equals mv squared over L plus mg. Thus, Ft1 is greater than mg by this term. Now we've proven it. We didn't have to show tons of math. We had to answer the question they asked. And so what they want us to do is to think bigger picture. And that's really hard to do because sometimes they ask for this and sometimes they ask for this. But make sure the things you're doing answer the question. So you may be thinking, well, what would the question have said if I needed to do the blue part? Well, that would be solve or find an expression for the force tension when the mass is at the bottom of the swing. This would be a solve or expression question. This was just argue, show that the tensile force that you had at the beginning would have to be bigger than the tension at the end. Okay? All right. That's all for today. We're going to spend the rest of the week reviewing. Okay? So, and then we'll spend, I'm going to give you another day on conservation of energy and work, give you some more problems that are a little more AP-ish. And then Wednesday and Friday, we'll go back and do some force problems and some kinematic stuff. And then next week is your test. And I'll give you a little bit more information about your test before we get there. Okay? All right. Have a great day.